Hello students, in this video I would like to discuss about heap sort. So first of all we look into some definitions. So first one is complete binary tree. A complete binary tree is a binary tree in which every level except possibly the last is completely filled and all nodes are as far left as possible. So complete binary tree is nothing but a binary tree. Binary tree means each node can have maximum of 2 children. So in complete binary tree every levels are filled except possibly the last, and in the last level the nodes will be towards the left. So that's the definition of complete binary tree. Next is heap. Heap is a complete binary tree. So heap can be of two types, max heap and min heap. In max heap the value of each node is greater than or equal to its descendants. So this is example for max heap. Each node is greater than the value of its descendants. So 17 is greater than all other elements, 15 is greater than 6 and 10, 10 is greater than 7. So next is min heap. In this one the value of each node is smaller than or equal to its descendants. So here is the example. Here we are studying heap sort. So heap sort uses max heap. Next is array representation of heap. We all know how the binary trees are represented in array. The same approach is used here. The root is stored at array index 1. If a node is at index k, its left child will be at index 2k and right child will be at index 2k plus 1. If a node is at index k, its parent will be at index position floor of k by 2. So here in this example the root is 16, so it will be stored in the first index position. Left child of root will be stored in index position 2. Right child of root will be stored in index position 3. Similarly for any index k, its left child will be at 2k. For example, here 8 is stored at index position 4. Its left child is 2 and it will be stored in 8. 2 is stored in 8. And right child will be stored in 2 into 4 plus 1, that is 9. The element 4 is stored in 9. So similarly, to find parent of 4, its index position is 9. 9 by 2 is 4.5. Floor of 4.5 is 4. That means parent of 4 is 8, which is at 4th index position. So next we look into some properties of heap. So if a heap contains n nodes, the height of that heap can be considered as floor of log n. Here we have 10 elements. Log 10 is 3 point something. Floor of 3 point something is 3. So the height of this tree is 3. We already know the definition of height. So next property is number of nodes with at least one child is floor of n by 2. In this heap, what's the value of n? Value of n is 10. 10 by 2 is 5. So 5 nodes can have at least one child. So total 5 nodes are actually parents. So the nodes at index position 1, 2, 3 to 5 are actually the parents in this tree. Next point is, in array representation, nodes at indices 1 to floor of n by 2 will be parent nodes. So we already seen 1 to 5 are the parent nodes. Similarly in array nodes at indices floor of n by 2 plus 1 to n, that means remaining nodes. Floor of n by 2 plus 1 to n will be leaves. That means the nodes at index position 6, 7 to 10 are leaves. So just keep these properties in mind. Next we are going to study some operations on heap. So there are 3 operations. Maintain or restore the max heap property. Create a max heap from an unordered array. Sort an array in place. So for performing these 3 operations we have 3 different procedures: max heapify, build max heap and heap sort. First one is maintaining the heap property. Max heapify is an important subroutine for manipulating max heaps. Its inputs are an array A and index I into the array. When max heapify is called, it is assumed that the binary tree rooted at left of I and right of I are max heaps, but A of I may be smaller than its children, thus violating the max heap property. The function max heapify is to let the value at A of I float down in the max heap so that the subtree rooted at index I becomes a max heap. So again the key procedure in heap sort is max heapify. So here we have 2 inputs, A and I. A is an array. That array will represent a binary tree and also an index value I. So here we assume the left subtree of node A of I and right subtree of node A of I are already max heaps. That's the meaning of this sentence. When max heapify is called, it is assumed that the binary tree rooted at left of I and right of I. Here the input is I, so it will have some elements in its left subtree and also some elements in right subtree. We assume the left subtree and right subtree are max heap. But if A of I violates the max heap property, this max heapify will modify the tree in such a way that the entire subtree becomes max heap. So it will be more clear when we see the example. So I will come back to the algorithm later. Let's look at the call max heapify a comma 2. So here I value is 2. So this is the root of that subtree. It have a left subtree and also a right subtree. Here if you notice, left subtree follows max heap property and also right subtree follows max heap properties. Because here 14 is greater than 2 and 8, 7 is greater than 1. But this entire tree, the tree which is rooted at I, doesn't satisfy max heap property. So before going to the formal algorithm, I will just explain the steps. What we will do is, here we will find largest among these three elements. Here we will find largest among 4, 14 and 7. So 14 is largest. So 14 will be swapped with 4. 14 will be swapped with 4. So 4 and 14 is swapped. Now 4 reaches here. Again we will check whether left subtree of 4 is a max heap and right subtree of 4 is a max heap. Anyway, here we have only one element in left subtree, so it is trivially max heap. Here we have one element in right subtree, so it is trivially max heap. So again, what will we do? We will find the largest element among these three. So 8 is largest, so 8 and 4 will be swapped. 8 and 4 will be swapped. So now 4 didn't have any children. So now if you notice, this entire subtree become the whole tree, or the subtree where we applied max heapify becomes a max heap. So the thing is, first we compare these three elements, find the largest one, swapped with the root. So the root comes here. Again we apply the same procedure in this left subtree. Next I will explain this algorithm. Here we have two parameters a and I. A is the array and I value is 2. Here we have one thing, heap size of A, that means total number of elements in the tree. Total number of elements here is 10, so heap size is 10. I value is 2. Then I calculate L. L is nothing but index position of left subtree. So we already studied, if I is given, the position of left child will be 2i. So L is 4. So we know how to calculate right subtree, root of right subtree, that is 2i plus 1, that is 5. So here we have steps 3 to 7. So 3 to 7 is actually to compare these three elements and find the position of largest element. Here among these three elements, largest element is 14 and its position is 4. So anyway, L is 4, 4 is less than 10, so that condition is true. What is A of L? A of 4, 14 is greater than A of I. What is A of I? A of 2, so 14 is greater than 4. So the largest will be initialized as L. Largest is 4, position of largest is 4. Again one more condition is there, if R is less than heap size of A, 5 is less than 10, and A of R. A of R is A of 5, A of 5 is 7. 7 is not greater than A of largest because A of 4 is 14. So this will not work. So if you notice line number 3 to 7, it is only to find the position of largest element among the I node, its left child and its right child. So then line number 8 will execute. If largest not equal to I, if 4 not equal to 2, we will exchange A of I and A of largest. What is I? 2. What is largest? 4. So A of 2 and A of 4 will be swapped. A of 2 and A of 4 will be swapped. This 4 and 14 will be swapped. So I will get the second figure. Next again I am recursively calling max-heap5. Max-heap5 of A comma largest. So max-heap5 of A comma 4 will be called. So during that call I value will be 4, L value will be 8 because 2 into 4 is 8, R value becomes 9. Next this condition will be checked. L is 8, 8 is less than 10. What is A of L? Here A of 8 is 2, 2 greater than A of 5, 2 greater than A of 4, that is 4 is false. So it will execute this else condition. Largest is I. So largest is 4. Then it will execute line number 6. R is less than or equal to heap size of A. 9 is less than or equal to 10. So this condition is satisfied. We will test this condition. A of R is A of 9. A of 9 is 8. 8 greater than A of largest. A of 4. A of 4 is 4. So largest is R. So now largest, the value of largest become 9. So what actually we done here is we just compare these three elements and find the index position of largest element. Next exchange A of I and A of largest. A of 4 and A of 9 is swapped. A of 4 and A of 9 is swapped. So it will come here, 4 will come here. Then again max-heap5 of A comma largest is called. So now I value is 9, L value is 18, R value is 19. So this condition itself is false. So largest becomes I. So largest is 9 itself. Here this condition is false. So line number 7 will not execute. In this case, the first condition in these two if statements are false. So next I will check if largest not equal to I. Largest is actually now equal to I. So it will not execute these two statements. So the max-heap5 will terminate. So now the heap property is restored. So I hope you understood the purpose of max-heap5. So max-heap5 is applied to a particular node with just an assumption that left subtree is a max heap and also right subtree is a max heap. So if it is applied, the entire subtree becomes max heap. So next procedure is for building a heap. So it is used to convert an array A of 1 to n into a max heap. So here the input to this procedure, that means the input to build max heap procedure is an array which is of any order. N means length of A, that means length of array. We already studied this property. The elements in the subarray A of floor n by 2 plus 1 to n are leaves. That means here we have 10 elements. From 10 by 2 is 5, 5 plus 1 is 6. The elements from 6 to 10 are actually leaves. So leaf means there is no left subtree and right subtree. So what we do here is apply max-heap5 on elements between 1 and n by 2. Here we apply max-heap5 procedure only to elements from 1 to 5 because those elements have only the children. So this is the algorithm. Heap size is initialized as length of A. Length of A is 10, so heap size will be 10. So here the for loop will iterate from n by 2 down to 1. So initial value of I in this example will be 10 by 2, that is 5. So I value will be iterating from 5 to 1. And every step we are doing max-heap5 of A of 5. Next we will see the example of build max heap. So next we are going to see the example for build max heap. So first step is heap size of A is length of A. Length of A means length of the array. Length of the array is 10. So heap size is 10. So the I value will be iterating from n by 2. N by 2 is 5. 5 to 1. So the initial value of I will be 5. So next I am applying max heap 5 on a comma I. That means I am applying max heap 5 to this subtree. The subtree have only one left child. Since it have only one node, it is trivially a max heap. So here what we do is we will compare 16 and 7. Anyway 16 is larger, there is no swap will happen. So next I value will becomes 4. So max heap if I will be applied to this portion. Here we have three values, 2, 14 and 8. 14 is largest, so 14 and 2 will be swapped. Next I value becomes 3. So the max heap if I procedure will be applied to this subtree. Again we'll compare these three elements. Here largest is 10, so 10 and 3 will be swapped. So you will get this subtree. Next I value is 2. So here we are applying max heap to this subtree. We already made this as a max heap and this as a max heap in previous iterations. So here also we are comparing these three elements. Here 16 is greater, so 1 and 16 will be swapped. Next again the max heap 5 will be applied here, because we already studied max heap 5 will be recursively called in the max heap 5 procedure. So 1 and 7 will be compared. So 7 is greater, so it will be swapped. Next I value becomes 1. First we compare these three elements. 16 is greater, so 16 and 4 will be swapped. 16 and 4 is swapped. Next I am going to apply max heap 5 to this subtree. Here 4, 14 and 7 will be compared. 14 is greater, so 14 and 4 will be swapped. Next I am going to apply max heap 5 in this subtree. Here among 2, 4 and 8, 8 is largest, so 8 and 4 will be swapped. 8 and 4 will be swapped. So here I got entire elements in a max heap arrangement. So here also the important procedure is max heap 5 of a comma I. Next we are going to study the exact heap sort algorithm. Heap sort algorithm starts by using build max heap to build a max heap on the input array a of 1 to a of n, where n is length of a. We already studied the working of build max heap. Since maximum element of array is stored in a of 1, it can be put into its correct final position by exchanging it with a of n. We already studied in max heap the largest element will be in the root. So while sorting, what will happen? The largest element will go to the last position. So the largest element is actually in root, that is position a of 1. It will be swapped with a of n. If we now discard n from heap, that means the last element will not be considered as part of heap anymore. This is done by decrementing heap size a. Now the children of root remains max heap, but new root may violate max heap property. So these statements will be clear when we see the example. We can store the max heap property by calling max heap of a of 1. The heap sort algorithm repeats this process for max heap of size n minus 1 down to heap of size 2. So this is the pseudocode for heap sort. And the first step is build max heap of a. A will be a unordered array. So these are the steps. I will try to explain these steps with the help of the example. So this is our input array. This array is of no order. The first element is 4, second element is 1, 3. It is in unordered manner. I am going to apply build max heap of a. The same example you already discussed in build max heap. So after applying build max heap, we will get a arrangement like this. This is actually a max heap. Then what will we do? For I values, I to length of a down to 2. What is length of a? Here I have 10 elements. So for I values 10 to 2, we will do these steps. So next we see what happens when I is 10. So here I is 10. What I am doing? I am exchanging a of 1 and a of 5. I am exchanging a of 1 and a of 10. So this 1 and 16 will be exchanged. So 16 will come here, 1 will go here. Next I will reduce the heap size of A by 1. Now we reduce heap size of A as 9. 10 minus 1 is 9. So what's the meaning is, here actually the largest element is in the root. I just swapped with the last element in the array. Just consider this as an array also. So this 16 is placed in the last position. Then what I done is, I removed this 16 from the heap. How I removed? Removed by reducing the heap size by 1. Now 16 is not part of this heap. So heap size of A is heap size of A minus 1. Heap size becomes 9. Then we apply max heap of A comma 1. We just apply max heap of A comma 1 on this entire tree. But 16 is not part of this tree. So here A of 1. So the left subtree of 1. That means index position 1. This subtree is a max heap. This subtree is a max heap. After applying max heapify A comma 1, this entire tree becomes a max heap. So in the end, I will get a max heap like this, but 16 is not the part of this max heap. So now, among the remaining elements, 14 is largest. It reaches the root position. Its I value becomes 9. On 9, 14 will be swapped. 14 will reach here. Then I will remove 14 from the heap by reducing heap size. Again I am applying max heapify of A comma 1 in this tree. So I will get an arrangement like this. Now among the remaining elements other than 14 and 16, 10 is largest. It is in the root. Next I value becomes 8. Here 10 and 2 will be swapped. Exchange A of 1 and A of 8. And heap size will be reduced. 10 will be discarded. Again we apply max heapify A comma 1. So this remaining heap will be converted to max heap. Again these steps will repeat for I equal to 7. Here 9 will be discarded and the remaining part will be converted to max heap. When I equal to 6, 8 will be discarded and remaining part will be converted to max heap. When I equal to 5, 7 will be discarded, remaining is converted to max heap. When I equal to 4, 4 will be discarded and remaining part will be converted into heap. When I equal to 3, 3 will be discarded and remaining part are converted to max heap. When I equal to 2, we have only 2 elements. So this 1 and 2 will be swapped, 2 will be discarded from the heap. So now if you notice these elements, these are all sorted and we reach the end of the iteration because this for loop will iterate down to 2 only. So now the I value is 2. So now the elements are sorted. So this will be the output error. So this is the working of heap sort. Thank you.